Okay, guys, we are going to talk about solutions and miscibility, being able to stir stuff, and we're going to look at why things decide to become solutions, how quickly they can become solutions, and factors you can do to affect the rate of solution formation. Okay, so let's go ahead and look at it. We're going to cover a lot of vocabulary terms by doing this. So you might want to jot some of these things down, or maybe do like a freeze screen and then kind of write your own notes on it, whatever you want. So what is a solution? Solution is a mixture of substances that appear to be the same throughout. Solution is a mixture of substances that appear to be same throughout. This is what we call homogeneous. The opposite of that is going to be heterogeneous. Okay, so that's this right here. Hetero means different. Heterogeneous. Okay, this means it looks different throughout. It's very distinct. Can you think of a mixture of things that doesn't look the same from place to place? You may think of trail mix if you zoom in kind of closely. So you can kind of see here's some trail mix. It is a mixture, but if I were to take a random little chunk, like say like right here, if I were to pinch from here to here and pull this out, that'd be a banana. But if I were to pinch from here to here in a different spot, I would get a very different grouping of material based on my sample size, right? So that's something to kind of consider. Now, if I were to get like a glass of lemonade, right? If I were to get like a glass of lemonade. So if I were to take a thimble or like a small little sample container and take a sample of the lemonade here versus here, and I leave the lemon peels out, versus here, as long as I've reasonably stirred this in the recent past, no matter where I get my sample of lemonade out of this jug, I'm going to get the similarly tasting lemonade no matter what. So that's how you know that lemonade is going to be a homogeneous. Homo means the same, genus throughout, homogeneous mixture. So it is a solution, because no matter where I sample from, whether it's here, or even at the top, I should get something very similar in flavor. Now, if we let this sit for a while and the ice starts melting, you might notice from your experience that some components of the lemonade are going to settle at the top. The heavier stuff might go to the bottom, like the sugars and maybe like some larger lemon chunks or things like that. And it's no longer going to be a solution anymore. There are a couple of reasons why that happens, and that has to do with what we're going to talk about in a little bit, right? It has to do with the nature of the particles that were mixed together. Are they polar or non-polar? The temperature, gravity, density, all those things, right? So we're going to talk about that in just a second. Okay, let's get rid of this though. Okay, now what are the different components of a solution? We got the solutes. These are the smaller things typically that are dissolved into the solvent. The solvent is the greater amount. So if we're talking about our lemonade, so in lemonade, the water would be the solvent. The solute would be the sugar, lemon, etc., right? So it's all the stuff that you added to. I like to put a little bit of this in here too. Let's see. And lavender. Lavender lemonade. Try it sometime, folks. Back in my home island, Hawaii, there's this big lavender farm that's about 4,500 feet up in the mountains. Very, very beautiful. Very hard to breathe up there, but the temperature is kind of more similar to like Colorado because you're really high up. But yeah, anyways, these are the different solutes, the things that dissolve into the larger amount of substance. Okay. Is it a physical or a chemical thing to make a solution? Well, we're not talking about if I were doing a chemical equation to kind of show what's happening here, I might go, all right, got my lemon plus my water plus my, let's do sugar. When I get done, I am not making, so I'm definitely not making this. Lemon 2, H2O, and then C6H12O6, which is the chemical equation for sugar. I'm not making this, okay? I'm definitely not making this. When I'm done combining these things together, on the product side, I'm going to get these same three components separated by plus signs still. Okay, I have not really combined them. I've kind of broken down some of these and rearranged them a little bit, but they're not permanently combining. You know this because when you make lemonade, if you were to let it dry out for a while, if you were to let it dehydrate, if you were to let it evaporate, that water would leave. The lemon would eventually evaporate off with the sugar, or with the water, and you would have sugar left in the bottom of a pitcher. And you guys know that from making perhaps like too much tea powder inside your cup when you're mixing it. That stuff eventually settles out and leaves the solution. So because you can let it settle out through gravity and density, we know that it's a physical process. Okay, you are not making a lemonade compound. Okay, this is not a compound. Very important to write that down somewhere. Not a compound, which is a rearranging of atoms, and they're formed by molecular bonds, atomic bonding. Okay, so not a compound. Okay, they can be reversed. No new substances are being made. They're just kind of being added together in combinations. Here's some types of solutions. You have gas and gas. An example of that is air. A homogeneous mixture will be a soda, but this is important right here because I want to show you something. Okay, so look at these two examples of Coca-Cola here. You notice that when the cap is there and the pressure is constant, this is a really high pressure, so it's forcing some of these CO2 bubbles to stay in solution, even though they have a lower boiling point than the liquid that the soda is made out of. Okay, so right here, this is a homogeneous solution. This is a homogeneous mixture. It's a solution. When you open it, you see these bubbles that form here. Well, it's because the CO2 no longer has to stay in solution. It can boil out because the pressure has been released. Okay, so right here, this is no longer homogeneous. Right now, this is hetero. Okay, this is a heterogeneous mixture. Pretty cool, right? Right here, this is homogeneous mixture. Homo versus hetero. Okay, homogeneous mixture, aka also known as a solution. Okay, so if you don't get anything else out of this today, you need to make sure that you know the difference between these two things here. Okay. All right. Okay, so that was gas to gas. An example that would be the air you breathe. You didn't think you actually breathed just oxygen, right? And by the way, you don't breathe oxygen, you breathe molecular oxygen, O2. But with that, this is maybe only 20%, I believe, of the actual atmospheric component that you breathe in. A bigger part of it is usually going to be nitrogen, so that's N2. Okay, we just showed you this right now. Liquid to gas is water and air. This is when you have a humid day. Liquid to liquid, lemon juice and water, we've talked about that. Liquid and solid, pastry dough. So you've mixed water with a little bit of flour. Solid and liquid, that's going to be salt into H20, or as we call it normally, H2O. Okay. And solid to solid, these are going to be alloys, right? And a really popular one that you guys know a lot about is going to be steel. Steel is a mixture of iron and carbon, maybe a couple other things depending on the impurities. One that we make using mercury, Hg, is used to make something called an amalgam. And this is a mixture of metals too. The solution process. A solute dissolves into a solvent. This is the exam right here. Make sure you understand that this is the directionality of the physical process. Like dissolves like. So you can only have two things that kind of are similar to each other chemically in order to make a mixture, a homogeneous mixture, very easily. You've probably noticed some things dissolve better than others, right? So like lemon into water, sugar into water, versus something like olive oil and water, right? Olive oil doesn't mix very well because they're not very similar, okay? Dissolvable. What is solubility? The amount of a substance that can be dissolved in a solvent is called solubility. So some things are a little bit more soluble than others. So a bucket of soil might not be quite as soluble to lemon juice as like a bucket of water, right? Because they're similar. Okay, solubility depends on the nature of the substance, both solvent and solute. Solubility of a substance can be compared by measuring. So how are we going to do that? We'll show you in a second. Solubility is the mass of a solute that can be dissolved in 100 grams of water. 100 grams of water, just remember it's 1 gram per milliliter, so this is 100 milliliters of water as well. Okay, under a given set of conditions, temperature and pressure. These right here, super important. Make sure you get this. The temperature and the pressure are what is going to determine solubility. In fact, it's really just temperature, but by increasing pressure, because we have the gas laws that you'll learn in chemistry. By increasing pressure, it is a direct correlation or direct causality that temperature will also go up as well. It's like you get a bunch of little guys. I'm going to draw a bunch of little guys right here. A bunch of little particles here. A bunch of little particles here. They like to move around. That's kinetic energy. But if I were to squish these guys together and now move them in a higher density, let's undo that. And I'm going to move these guys over here. Now all of a sudden, they're going to bump into each other. This is a more crowded room, right? So the temperature is going to go up because what did I do is I've made that container that was once bigger into something that's smaller. And if you've ever been in a more crowded room and you're trying to move around, it gets hot pretty quickly. So the pressure is going to change the temperature. Okay, but you need to know that. No matter what I do to the substance, it is ultimately the overall temperature that's going to determine how much of that solute can dissolve into the solvent, and that can also be changed and manipulated by pressure. Like dissolves like. So we remember our ionic and covalent compounds. This is one of the applications of understanding what that is, right? The sharing of electrons versus the stealing of electrons or the borrowing of electrons. Ionic compounds will dissolve ionic compounds, so that's the way it works. Polar substances, usually charged covalent compounds, are able to dissolve other polar substances. This is the reason why you don't bond to your surroundings when you touch stuff. Your skin has two different polarities. It has a polar surface on the outer and inner surface. I'll show you right now. All right, so this is your skin if you were to zoom down to like the molecular level. So this is extracellular, which means this is the outside world right here. Stuff trying to get in. Can't really get in because you've got this hydrophilic head. So this is something that hydro means water, philic means love, so love of water. So it likes to be attracted to water, but things that are not polar in nature are not going to be able to get through because they're not going to mix, right? Mixing means that they're going to be able to come together and attach and then do chemistry, right? But if you aren't similar enough to actually trade those electrons, which we learned about in the last chapter, you're not going to have any hopes of mixing at all. Okay, once you are able to get through that, things don't get in because all of a sudden if you were mixable here, all of a sudden, look, you have hydrophobic tail. So now you're afraid of water. So let's say something that was water-like got into your skin, like you put some moisturizer on you. So you put some moisturizer on you, the water in there does chemistry with the extracellular surface. It mixes, enters your skin layer, but then look, right here, you have this water-hating, hydrophobic, fearful, and it pushes it back out, right? So it's kind of hard for a substance to do chemistry all the way down here. Your skin is a nice chemical barrier, chemical and physical barrier to the outside world. And another really interesting thing about skin is that it is actually your largest organ in your body by mass. Okay, largest organ in the body by mass. Crazy, right? Integumentary system. Learn it. Okay, intracellular inside, right? So things have to go through a lot of different checkpoints in order to be able to get inside your body through your skin. Okay, but that's what we were talking about with like dissolves like. If you're not similar, if you're not polar, you're not going to dissolve something else that's polar. Okay, water. Water is a universal solvent because it is polar. It has an end that has a charge. It has an end that has a positive charge, positive and negative charge. So all you got to really do is flip this bad boy around from here to here. And if you weren't able to dissolve something with the oxygen side, well, as soon as it flips around, guess what? You got the hydrogen side here. It's a positive side. So it might be able to do chemistry very easily. So something we're going to learn about in the next chapter is that if you put, let's see, sodium hydroxide. Okay, if you do sodium and add a hydroxide, OH is called hydroxide. This right here is called a base. If I go hydrochloric acid, HCl, this is an acid. If you put, generally speaking, if you put a hydrogen in the front, this makes something an acid. If you put a hydroxide on the end, it's called a base. What do you notice about the H and the OH? I could take these apart and put them together and make HOH, right? So it's an acid-like and it's also a base-like, right? So I can, technically speaking, have a chemical that is acting as an acid and a base at the exact same time. Well, this is just a really fancy way of saying, this is messy, right? But if I could recombine these H's, and how do I write that chemically? H2O. Isn't that crazy or what? So it's a universal solvent because if you break up the components of water, you end up with something that can turn into an acid or a base. And what do we know about acids and base? They're really good at dissolving stuff, right? Bases are really good at dissolving stuff. Like soaps. Soaps can saponify bacteria and dirt and your oils in your skin. They are able to bind and wash away so easily because they're similar, right? Yeah, moving on. Help, I'm dissolving, but bears are insoluble. It's easy for you to say, you're not polar. So that's great, right? So you're in the North Pole. You get the joke? You get it. Come on, you get it. Come on, man. Just say you get it. You get it. So this is a worksheet you'll have to end up doing at some point, or you'll have to answer on a Socrative. But we're looking at the solubility curve. So this is grams per 100 grams of H2O. And so let's look at our axes. We've got solubility. So this is 0 grams all the way up to 100 grams of a solid or a liquid that we're going to try to dissolve into water. And then on the x-axis we have temperature. So what do we notice about the heating and its effects on solubility? Well, calcium chloride, as I start increasing the temperature from 0 to 10, I go from a little under 60, we'll call it 58, up to about 65 grams per 100 milliliters or grams of water. Okay, you can see that this is kind of an exponential rate of growth. As it gets hotter, I'm able to dissolve a lot, and it looks like I'm approaching some sort of asymptotic value. So it means at a certain point, it doesn't matter if I raise the temperature any higher, I'm not going to be able to dissolve calcium chloride at a higher rate. Okay, so eventually it's going to plateau. Or yeah, potassium chloride looks like it's much more of a linear. So as the temperature goes up, I'm able to increase my solubility. In fact, let's see. So I go from 30 to 40, 30 to 40, from 15 to 25. So every 10, it looks like I'm going up, more or less. Okay. The only one that doesn't really seem to be dissolving more liquid as you get hotter are sodium chloride, because sodium chloride looks like it plateaus. So this is kind of reaches a horizontal asymptote, which means it's a horizontal line that it can't hit. Looks like it's just going to find its limit there. And then cerium chloride, which has a limit. It actually decreases solubility the higher temperature you go. But that's how you read these. Very important skill, just to be able to read a graph. Definitely not specific to just chemistry. So know your graphs. How to change solubility. Well, let's see. What do we think the effect? I want you to kind of pause this and think. Make a prediction. If I stir a solid into a liquid, we see that my solubility rate, okay, this is not necessarily solubility. If I were to put sugar into water, let me make sugar water, right, and left it there for 3 hours, it would have the same effect as if I were to go in with a stirring rod and start shaking that bad boy up, right? Like, right? I'm not going to be able to dissolve more of that sugar in just because I'm stirring it. But what it does do is it increases the rate at which that would dissolve. So we're talking about a rate here, okay? For all intents and purposes, you could go ahead and memorize it and understand that stirring increases solubility, but really it's the rate of solubility we're talking about. Grinding and stirring are going to have a very similar effect. Why does it increase solubility? Well, I could take that sugar I was talking about earlier, right? And I can leave it like this. Let's see. I'm going to put a versus here, okay? So this versus this. I could do this, right? I could leave the sugar as a big old cube and let it wait for a long period of time, right? Lots of time. Or I could grind it up into lots of little teeny versions of that cube, and now there are a lot of surfaces. I've increased the surface area. I've increased the surface area by grinding. And so now there are more surfaces to be able to do chemistry easily, right? So instead of having to like worry about cutting this top layer, doing chemistry with all just this top layer first, right? So I'll go ahead and show that. I'll highlight what I'm talking about, right? So instead of having to wait for this entire surface to get used up first, and then I have this new surface after that's gone, and I have to do chemistry with that surface. Then when that's gone, I do chemistry with that surface. Well, instead of having to do that, every single one of these things can do chemistry all at the same time, right? And so they're able to mix a little faster, right? It doesn't mean that I'm going to mix more, it just means that it's going to mix faster. Why does stirring increase it? Well, you're doing two things now. You've made this cube into these guys here, and you're also moving them around all over the place, and you're finding them new partners to do chemistry with. You're finding new water molecules to do chemistry with, right? So that's pretty neat. Okay, temperature. This one definitely increases solubility, as you saw from the last slide. The solubility, the amount of stuff that you can stick into a solution, goes up because the temperature goes up. And why would that help with the solubility? Well, you're increasing the kinetic energy, the bond energy. You're going to break the bond energy of the solvent and solutes. Okay, and pressure solid into liquid, doesn't matter if I have a higher or lower pressure. That's going to maintain constant. Okay, gas into liquid though, let's look and see what happens in the next slide. Pause it and make a prediction. What do you think is going to happen if I stir a gas into a liquid? So I take some gas and I stir it into a liquid solution. Okay, think about what grinding is going to do. Can you even grind gas into liquid? Temperature. What does increasing the temperature of a gas mean for its solubility in liquid? And what does pressure do for a gas in liquid? So I want you to think and predict. Okay, so it turns out stirring does a little bit of both. I can increase the rate of dissolution or dissolving into a liquid if I stir it up. But as you can imagine, if I start shaking up some sort of liquid substance, I can perturb the gas molecules in there and they can escape. Okay, grinding can't really do that. Temperature, if I decrease the temperature, the chances that it'll stay in solution are higher, right? Because remember what I told you earlier at the beginning of the video? If I have a Coca-Cola and I open up the top, the gas molecules inside, the CO2, are going to want to escape because they boil at much lower temperatures than water does. The water has a boiling point of 100 degrees Celsius. The boiling point of CO2 in Celsius is negative 78. Okay, negative 78 degrees Celsius. Compare that to water, again, 100 degrees Celsius. It's going to want to escape that jar very, very quickly, right? So you want to keep that temperature really low because gases are gases, right? They like to rise when temperatures are high for them, and they go really, really high, up, up, up. So if you keep the temperature low, it's going to make the rate of solution much higher, okay? Okay, so if the temperature's up, you're not going to be able to keep those gas molecules in. Okay, pressure, when we increase the pressure, we're going to increase the rate of solution formation, right? Because you're pressing those molecules into, those gas molecules into the liquid. And you saw that with the soda. Soda is a very, very good example. So when in doubt, I want you to think about soda. Okay, think about a soda can closed. Soda can closed. Okay, here's the pictures of what we were just talking about right there. Okay, so right now, the molecules probably want to be like this. So this is, let's say, a soda in an open room. So this is with the can or the lid open. So when it's open, you have some particles that are going to remain in solution, but then you have a bunch of them that are escaping, they're going away, they're going in. When I increase the pressure though, so step 2, now look what happens. I have less of those molecules floating around freely, and more of them are stuck in solution. So this would be like the soda can closed. So I put the lid back on, or put the bottle cap on. Okay. Okay, the effect of solutes. All solute particles affect the physical properties of the solvents. Adding solvents lowers the freezing point of the solvent. Adding solutes lowers the freezing point of the solvent. Adding solutes raises the boiling point of the solvent. Okay, and why is that? Well, imagine how you feel when you're hungry and tired and you don't have a lot inside you, right? You haven't eaten. Well, you're going to feel really sensitive to temperature changes, right? You're going to get cold at a much lower temperature, right? Same thing here. It's harder to freeze you if you have a lot of stuff in you, though. So you're gonna be a little bit more impervious to the cold if you have more stuff in you. So think of solutions the same way. If I have a glass of water, that might be a really horrible drawing of a glass of water, but whatever. Okay, let's say I have a glass of water here, and this thing freezes at 0 degrees Celsius. But then I go ahead and do this. And I've added some other junk to it, right? Well, now, in order to freeze this bad boy, I got to freeze all the blue stuff, and I got to freeze all the green stuff, right? And the green stuff, these guys, with their powers combined, make this temperature much lower. Maybe I'm going to go to negative 30 degrees Celsius, right? Who knows? Same thing here when you're trying to boil something, right? If I take these glasses, and I just have a glass of water, well, the boiling point here when I add heat to it is going to be 100 degrees Celsius. But if I add that green junk back to it, certainly you can understand that it takes more energy to heat up everything in this solution, right? Now all of a sudden, perhaps my boiling point is like 120 degrees Celsius. And you've seen this before, or at least you know the fact that if you add this compound, NaCl, plus H2O, this is salt water, right? The boiling point is much higher, or it's higher, right? The boiling point goes up. It turns out you have to add like 6 pounds of salt or something like that to like 10 gallons of water to get an appreciable difference in boiling temperature. So don't do that thinking you're going to be able to boil spaghetti noodles at a higher temperature, or you're going to be able to cook something faster. You have to add a considerable amount of salt. Versus just cooking it for a little bit longer. So really, when you're salting the water, you're just adding flavor more than anything. But nonetheless, it works. If you want to do a little home experiment, I wouldn't play around with like the heating stuff. Yeah, don't do that. No boiling. Let's not mess around with that. I don't want anybody to get injured. But you can definitely test this freezing thing here. So you can take some water, and you can put it in a jar that's not going to crack if you put it in the freezer. Maybe like an ice tray. An ice tray would be great. And then you can do another... ice cube tray and put maybe a little bit of rubbing alcohol in some of the water that you put in that one. So you have 2 separate trays. This one just has H2O. And then your second tray, you put H2O plus alcohol, rubbing alcohol. Maybe like half and half here. Make sure your parents are helping you out and you're not like, you're not going to piss anybody off or anything like that. And just kind of check it maybe every 30 to 40 minutes, and then look at the crystallization of the H2O versus the H2O plus water. If you ever had your parents put some sort of adult beverage in the freezer, you notice that it doesn't freeze over, and that can kind of attest to that, because those adult beverages have water in them, but they also have other stuff in them, so it increases the freezing temperature. That's part of the process of putting antifreeze in your car, right? The antifreeze means that the engine block won't freeze over, the gasoline won't freeze over, the water lines won't freeze over. It doesn't really make sense for us here because we don't really ever have to worry about that. But if you move up to like somewhere like Chicago, or you go to central Canada in the winter, they literally let you out of work every so often so you can go start your car so it doesn't freeze over, right? Because that happens. So it's part of what we do. Also, salting the ground does that. Salting the ground in the winter when you have snow, it'll do that, because when you mix salt and those solid water particles or ice, you end up increasing the freezing, you increase the freezing point and therefore the melting point as well. So I hope this was helpful. I hope you can start seeing all of your different chemistry things that we've learned about this year, your physics things that we've learned about this year, kind of coming together in a more macroscopic or big picture kind of way. Okay. email me or send me a reminder, send me something on Classroom if you have any questions. Thank you.